Okay, today I'm going to give you a crash course in antiderivatives. It's a lot of sections. I'm going to be blending a lot of different things together here, okay? So I don't want to say this is chapter this, just antiderivatives. All right, so what we've seen, in Cal 1, a lot of it was the derivative, taking a function, finding its derivative. In Cal 2, what we want to do is the reverse process. We want to go and start with a function and go backwards. Say that's the derivative of something. What is it the derivative of? So let's look at a couple of examples. If I tell you right now that the derivative of some function is 2x, can you tell me what that function was? X squared, right? Is that the only one it could have been? Yes and no. I could have done x squared plus 1, or I could have done x squared minus 4, or I could have done x squared plus 10, or as long as there's a constant there, right, being added, then the derivative of that constant would have gone away. So what we would say is something like this, plus capital C, some constant. And that actually takes care of all of the possibilities, doesn't it? C is some constant, so we'll put that next to this. C is a constant. We don't know what it is. So realistically, when you think about this, let me see if I can bring up my visual demonstration here. Come on. I don't have it there. I apologize. Thought I had that right there. There we go. So here it is. If f of x is 2x, right? Sorry, that's the derivative. Then we said that the antiderivative, right, where it came from would have been x squared plus c. Forget this notation for a second. So this is what 2x looks like, right? A line. We're saying that the function that it comes from, right, it can be x squared, but any constant. It can be any of these, right? Any of those. So what we actually get is an entire family of functions, right? All of those functions, all those parabolas would be a function that 2x could have come from, yes? And the connection that we want to make is that the slope of the tangent line, right? Remember, if you have a function, the slope of the tangent line is the derivative. What we're saying is that if you take this function or this function or this function or any of those, and you look at the slope of the tangent line at a certain x value, it's the same slope for all of those, isn't it? All those little tangent lines have the same slope. Yes? Okay, so this represents, this is a family of functions. So there's not just one answer. But there has to be some better way for me to ask you to find an antiderivative, other than me say, find the antiderivative. So we need to introduce some new notation here, all right? First, we'll define what an antiderivative is. So definition. Capital F of x plus c is called the general antiderivative the general antiderivative of little f of x if the derivative of capital F of x equals little f of x. So we're using capital F's and little f's here. The capital F function is the antiderivative function. It's called the antiderivative function because the derivative of it gives you the little f. So what was capital F here for us? What was capital F here? X squared plus c, and the little f would have been this 2x. Did y'all get that? Do I need to go back? Yes? So let's try a couple of examples. Find the general antiderivative okay, and I'm going to do a couple of them. A, little f of x equals cosine x. What is it? Sine x. So you're telling me capital F of x should be sine x, not negative sine x, right? The derivative of cosine is negative sine, but that's not what we're asking. We're saying cosine came from a function that we took a derivative of. What did we take derivative of to get cosine? Sine. But not just sine x plus c. And we always throw this constant on. Every time we find an antiderivative, we always throw the constant on there. Some instructors are very particular about that. If you leave it off, they take off, like they count it like it's completely wrong. This constant right here is also known as the constant of integration. But we haven't really talked about what integration is yet. I'll try and get to that today if I have a chance. All right? But if I don't, I just want you to have heard that before. The C is called the constant of integration. Everyone clear with that? Now, your ability to get that relied on your knowledge of derivatives, right? You had to know that the derivative of sine of x is cosine x for you to get that. If you didn't know that, what you gonna do, right? Okay, how about this one? Little f of x equals negative cosecant squared x. What is it? The derivative of tangent x is secant squared x. Good try. Cotangent x. Cotangent x plus c. So how could you figure that out from your formula sheet? You could go to your formula sheet, you could look at your derivatives, and you could be looking at the right side of the equation. You could be looking over there for what? Negative cosecant squared x, and you would see that it's the derivative of cotangent, right? All right, let's try another one. Little f of x is 1 over x. Natural log, ln x. That's what you said, right? Okay. Plus c. Why? Because the derivative of the natural log of x is 1 over x. Again, relying heavily on your knowledge of derivatives. Relying exactly on your knowledge of derivatives, right? You have to know that to be able to go backwards like that. How about this? Little f of x equals 1 over 2 root x. Capital F of x is square root of x plus c. Again, why? Because I tried to drill into you that the derivative of the square root of x is 1 over 2 root x, right? So far, it looks like to find antiderivatives, you really have to know derivatives. Yes? But that also means that it seems like I can only give you things that you know the derivatives of, right? Like, how about this? Hmm. Now, we know the derivative of tangent of x, right, is secant squared x, but that's not what's being asked here. So what do you take the derivative of to get tangent? It's not there, right? It's not there? We never did that, did we? Now, let me tell you what it is, and then we'll check it. Negative natural log cosine x. Why? Well, the negative, let's take the, plus c. Let's take the derivative of this real quick. The negative in front, just ignore it for a second. What is the derivative of the natural log of something? 1 over it, right? Now let's put that negative back in. That's 1 over it. Then chain rule says times derivative what's inside. What's the derivative what's inside? Negative sine x, right? Derivative cosine is negative sine. And what's negative 1 times negative sine? It's just sine. And sine x over cosine x is tangent x. Now how would you have known that? You mean rewrite it as sine over cosine? That's exactly the way you would do it. But even then, how would you know to go back to natural log? It's a little tricky, isn't it? There's got to be a way that we do that, right? There has to be some like systematic approach, which there is. Okay, so all I'm doing here is illustrating it's not easy to go backwards necessarily unless you know real quickly where it came from, right? So something as harmless as tangent is somewhat challenging to go backwards from. You all understand? Agree? Yes? Okay, so let's deal right now with just the things that we can handle easily. Let's work with just that. The first problem I gave you was 2x, and everyone said x squared, right? Because everyone knew that the derivative of x squared was 2x. Maybe you can do that for any power of x. Maybe there's an easy way to go backwards. Let's try this one. How about little f of x? Oh, put a question mark up here like, you know, kind of like, yeah, how would I have known that, right? How about this? How about 3x to the 4th? So let's try and think backwards for a moment. This is a power function, isn't it? It's a power of x, x to a power. We know that when we take derivatives of x to powers, what happens to the power? Comes out front, and then the power does what? Comes down by 1, right? So if we're going to go backwards, that power is going to actually have to go up by 1, isn't it? So I can tell you right now, I think you would agree with me, hopefully, that the capital F of x that we would be looking for would have to have an x to the 5th power. Yes? Now, is this right by itself? Let's see. Let's take the derivative. What would happen? 5 would come out, and it would be x to the 4th. That would give you the x to the 4th, but now we have a 5 in front. I don't want that 5 in front. What do I want? The 3. Now, the 3, though, should just carry along with us, right? When we take derivatives, constants in front can just carry along. So why don't I stick the 3 out here? That'll make that 3 appear in the derivative, won't it? But what do I need out here to make it so that when the 5 comes out, it does not screw things up? Close. 1 over 5. 1/5. Do you agree? If I do the 3 and then the 1/5, then the x to the 5th, the 3 will just come with us. The 1/5 will kill the 5 off when it comes down, and then the power will reduce by 1 and I get to 4. And then I throw my constant on here, which I could say this is really what, 3/5 x to the 5th plus c? 3 times the 5th is 3/5. Now, there is good news with this. You can always check your answer, right? By just taking the derivative. If your derivative turns out to be this, you're good. Not asleep. How you doing? Okay. Okay. Today's been texting day. A lot of students have been texting today. I guess end of semester rules don't apply anymore, I guess. All right. There's only like 3 students in here that could text right now and I wouldn't care. There's probably 3. That's it. But they won't text because I know they're not that type of student. So, all right. How about this? Square root of x. Now don't say 1 over 2 root x, okay? Because that's not the way we're going with this, right? We're going the other direction. So let's start with this. Let's rewrite it as a power because it is a power of x, right? I need the 1/2 to be there, right? I realize that, again, the power when I take derivatives comes down by 1. So when it comes down by 1, I need it to turn into a 1/2, right? So what do I need to start with that when I subtract 1 from it, I'd get 1/2? 3/2, right? 3/2. So I know this much. I need x to the 3/2 up here. Right? That's 1 more than this. I'm just adding 1 to 1/2, right? That's all I'm doing. Adding 1 to 1/2. 1 plus 1/2 is 3/2. But will this work by itself? No, because when I bring this out, right, to take the derivative, I have a 3/2 out there. What do I want out here? A 1. So how are you going to get rid of a 3/2 and turn it into a 1? Multiply by 2/3. Right? Multiply by 2/3, and that should kill off 3/2. So 2/3. Does that seem like that'll work? Just plus c, and we're good. Are y'all okay with this or not? Question? Just leaving it? No. Which is why we try and stress in like college algebra, like radical notation, and we kind of don't like working with it because rational exponents are easier to work with in calculus. Okay, GH, how about this? How about we try to find a general formula. What do you say? We try and find a general formula. I mean, we knew for derivatives, the formula was that the power came out and then we subtracted 1, right? That was the formula for taking a derivative. But going backwards, let's see what we would have to do. If we have a function that is a power function, x to a power, what will the general antiderivative have to look like? So can you tell me what the power on the antiderivative is going to be? N plus 1. I know I'm going to have a plus c out here. When I take the derivative of this, the n plus 1 is going to come out, right? And I don't want anything out here except a 1. So how am I going to get rid of an n plus 1? 1 over n plus 1. Very good. 1 over n plus 1. is a number out front. So just check this for a second. If 1 over n plus 1 is a number, then if I bring the n plus 1 out, the n plus 1 over n plus 1 will cancel. It'll become a 1. The power will come down by 1 and become an x to the n, won't it? And that should work for any power of x. I mean, yeah, any power of x except what power? For what value of n is this thing not defined? If n is what? 0 is okay, because I can plug 0 in here and 0 in here. -1. That's the only power of x n this won't work. Power of x this won't work for. If I put a -1 here, my formula says what? 1 over -1 plus 1. What's -1 plus 1? 0. 1 over 0, undefined. So the only problem I would ever have here is if n is -1. So let's put over here for n not equal to -1. That formula should work. So what if it is? What if it is -1? What's x to the -1? Isn't it this one? That's x to the -1, isn't it? And in the case that it's -1, it's really 1 over x, and the antiderivative is what? Natural log of x plus c. So even for the case that it's -1, our formula won't work, but we still know what the antiderivative would be. So do you see that we have x to any power covered right now for any power? This is called the power rule. Power rule for antiderivatives. Not to be confused with the power rule for differentiation, which would be the n comes down, subtract 1. This is the reverse rule, but it's still called the power rule because it involves powers of x. I mean, I guess you could, but books won't call it. They call it power rule for antiderivatives. All right, so let's try another example. What if little f of x is equal to 5x to the -2? Oh, no. Let's go 5x squared plus 3 over x squared plus 5 minus 4 cube roots of x. What's that? That's it. X to a power, right? Okay, so before we do that, though, do you remember when we were taking derivatives? If you had sums and products, sums and differences, so pluses and minuses between functions, you did derivative of each one, right? Each one. Same with antiderivatives. When you go backwards, if you have terms, you can find antiderivative of each term one by one, all right? So let's, as was suggested, let's first rewrite everything as a power of x. 5x squared, I think that's in good shape. I don't think we need to rewrite that. But the next one should be rewritten how? I need it as x to a power. 3x to the -2. You cannot leave it down there as an x squared because now you have a quotient, right? If you leave it there, it's a quotient. And how do you undo a quotient? We haven't talked about that. We know taking the derivative of a quotient sucks, right? Quotient rule? So imagine going backwards is going to suck even worse, and it does. So we have to first make it look like a function by itself. The constant in front is okay, because it's just going to carry along with us as we go backwards. Then what about this? You could look at it if you want 5. You could write x to the 0 if you want. You don't need it. But I'm going to put it there just so we have it. Minus 4x to what power? 1/3. And now I get to apply my power rule on each of these 4 pieces. So here we go. Antiderivative, capital F of x, equals 5 comes with me. My formula is, excuse me, capital F of x, 1 over n plus 1, x to the n plus 1, plus c, right? If little f of x is x to the n, there's my formula. So for me, I've got here x to the n, so x squared is x to the 2. So this is going to be times 1 over 2 plus 1, x to the 2 plus 1. Yes? I'll figure that out on the next line. The next one says plus 3. And then what's the n for this one? Negative 2. So times 1 over negative 2 plus 1, x to the negative 2 plus 1. The next one, I don't really like this x to the 0. This one I think is one of the ones that you just know, I hope. What do you take the derivative of to get 5? 5x, right? You don't need to like think through power rule here, right? So that's just 5x. And then what about this last one? Negative 4. And then what's the power is 1/3, so I'm going to have to do times 1 over 1/3 plus 1, x to the 1/3 plus 1. Then I'll have plus a c out here. I ran out of room. Any questions on where any of that came from? Let's clean this up. 1 over 2 plus 1 is 1/3 times 5. 5/3. X to the 2 plus 1 is 3. 5/3 x cubed. Okay, how about this one? 1 over negative 1, which is negative 1. What's negative 1 times 3? Negative 3. X to what power? Negative 1. Negative 2 plus 1. Plus 5x, nothing happens here. All right, let's try this one. Oh, great. What's 1/3 plus 1? 4/3. What's 1 divided by 4/3? Flips over and becomes 3/4, right? 1 over 4/3 is 3/4. What's 3/4? What's 3/4 times negative 4? What's negative 4 times 3/4? What is it? Negative 3. X to what power? 4/3. So that I just did 1/3 plus 1 is 4/3 plus c. You could, if you want, rewrite this term right here. It would not be wrong, but it also would not be more correct to write that as negative 3 over x. Bless you. And like I said, you can always check your answer, right? Well, let's just check real quick. And I say real quick. Take the derivative here. 3 comes out. 3 cancels. You get what? 5x squared. That's encouraging. All right, here, bring out the negative 1. Negative 1 times negative 3 is 3. X to the, subtract 1, negative 2. There we go. Here, derivative 5x, 5. Okay, 4/3 comes out, hits negative 3. The 3's cancel, you get negative 4. Then you subtract 1 from this power. 4/3 minus 3/3 is 1/3. Good. It works. You all right with that? Plus c. And the derivative of c would be 0, so we're good. Now, I want you to pay special attention here to this problem, okay? Students always make this problem so much harder than it has to be. And a lot of you did this on the test when I gave you that and told you to find the derivative. You made it harder than it had to be. A lot of people, when I gave this on a test and said, find the derivative, go forward, Cal 1, everyone tried to do quotient rule on it. Instead of breaking it up, because you have only one term in the denominator, right? You can do x squared over this over this, this over this, this over this, right? Break it into 4 separate terms. You can only do that because you have one term in the denominator. Same thing is going to happen when we try and go backwards. Let's first break it into 4 separate pieces, then do the antiderivative. So let's break it up. And I'm going to take my time. X squared over 3 root x plus 2 over 3 root x minus root x over 3 root x plus x over 3 root x. Right? That is a legal move. I can do that algebraically, no problem. Could I do that same thing if these were flipped over? If all 4 of these were on the bottom and this one was on top? You could not do that. Now I can rewrite this as, let me see if you can follow this, 1/3 x squared over x to the half plus 2/3 times 1 over x to the half minus 1/3 times x to the half over x to the half. Didn't really need to do that. Plus 1/3 times x over x to the half. So what I'm doing is I'm kind of pulling everything apart to make everything powers of x. I rewrote all my roots as x to the 1/2, right? Everywhere I saw square root of x. When I had a constant, like right here, 3 on the bottom, I rewrote that as a 1/3, because it is, right? 3 on the bottom is the same as 1/3 out front. 2 over 3 is the same as 2/3 out front. This is like a negative 1/3. This is like a positive 1/3. Are y'all okay with that? Now let's just rewrite these. I haven't done any calculus yet, right? This is all algebra at this point. 1/3. Okay, what is this going to become? X to the 3 halves. So you're doing 2 minus a half. That's the same as 4 halves minus a half, which is 3 halves. So that becomes x to the 3 halves plus 2/3. How can I rewrite this one? Right here. X to the negative half minus 1/3. How do I rewrite this? Just 1, right? They cancel out. These just can't, they're the same thing, right? Anything over itself is a 1, so that's just going to become 1/3. And lastly, 1/3 x to what power? 1/2. Because that x on top is like an x to the first power. 1 take away a half is 1/2. Does everyone agree all I'm using is properties of exponents, rules of exponents? No, there's no calculus yet. Now the calculus, okay? So now, actually, I'm not doing a set problem. Here's capital F. So capital F of x should be 1/3 times, and I'm working on this one now. So n is 3 halves. 1 over n plus 1. X to the n plus 1. That's just this first one. Now you get to a point after you've done enough of these where you don't have to write all the detail down. Where you just sit here and you look at it and you say, okay, when I add 1 to that, it's going to be 5 halves, isn't it? 1 over 5 halves is 2/5. 1/3 times 2/5 is 2/15. And it's just, I mean, you're doing it all mentally. The sooner you get to that point, the easier Cal 2 is going to be. All right? You do not, if you If it takes you 3 months in calculus to get to a point where you don't need this, you're working way too slow. You've got to have that mastered like within the first 2 weeks, where all the fraction stuff's happening up in here instead. But I want to make sure you see where you know, the mechanical part of what you're doing. Are there any questions? All right, let me do the next one. Plus 2/3, 1 over, what is it, negative 1/2 plus 1? X to the negative 1/2 plus 1. What's the antiderivative of negative 1/3? What's the antiderivative of negative 1/3? Negative 1/3 x. So if you ever see a constant, the antiderivative is the constant times x, right? And then the last one, plus 1/3, and then here comes the 1 over n plus 1. 1 over 1/2 plus 1, x to the 1/2 plus 1, and then plus c. I keep running out of room. Got all this room over here. Oh, well. Okay, who wants to tell me what they got? Like final answer. Anyone want to volunteer their work? No? Okay. What's 3 halves plus 1? 5 halves? What's 1 over 5 halves? 2/5. This is 2/5. 2/5 times 1/3, you multiply straight across, is what? 2/15. X to what power? 5 halves. Okay? Plus, let's see, what's negative 1/2 plus 1? 1/2, 1 over 1/2, 2. 2 times 2/3, 4/3. X to the 1/2. Minus 1/3 x. 1/2 plus 1, 3 halves, 1 over 3 halves, 2/3, 2/3 times 1/3, 2/9. X to the 3 halves, plus c. Kind of got the hang of it? Practice makes perfect, all right? You just got to practice. It's not enough to sit here and be like, yeah, I could do that, and not go through and get your brain working with it. All right. So, that's power rule. Let's get back to that tangent problem now. Well, you know what? Before I do that, let's get some new notation, because I get tired of writing this capital F of x. Notation. Given f of x and asked to find capital F of x plus c, in other words, if you're given a function and asked to find the general antiderivative, we can use a special notation. And here it is. This is like a stretched out S, okay? I'll tell you what it's called in a second. You put little f of x here, and then next to it times, you put this thing d, little dx. This is equal to capital F of x plus c. In other words, this notation tells you this. If you see this symbol with the little dx sitting there on either side of your function, that is telling you to find the general antiderivative. So from now on, I will not be writing down, here's little f, find capital F. I'm just going to write that symbol. I'm going to write the function. I'm going to put a little dx next to it, and that's going to tell you, go find the general antiderivative. Now, these symbols have names. This is called the integral sign. The function that is inside that you are trying to actually find the antiderivative of is called the integrand. That's kind of like when you had a radical. The thing underneath the radical was called the radicand. The thing inside the integral sign is called the integrand. And this right here is your differential. And you will see how important that differential is in just a moment. Right now, the differential for us means the derivative of x. And what is the derivative of x with respect to x? 1, right? So this is really like a 1, but we need it, as you'll see as we advance through this, okay? The differential kind of keeps track of what the variable is. The process of finding antiderivatives is called integration. So a lot of times you'll hear, like, in descriptions for courses, you go register at a university or somewhere, and it'll say like differential calculus. Differential calculus is Cal 1. You're doing derivatives, differentiation, right? Differentiation, differential calculus. And then you'll see another course and it'll say integral calculus. And integral calculus is integration. That's Cal 2, right? So integration is backwards process from differentiation. Yes? Well, in Cal 3, you don't do either. Well, you're doing a mixture of all this. But there's really only differentiation one way and then anti-differentiation or integration the other way. So there's not a third thing that you'll do in Cal 3. The big thing in Cal 3 is that now you extend it out into three-dimensional space. Everything we do in Cal 1 and 2 sits on a flat piece of paper, right? All right, so we got the integral sign. Now, I'm not real happy with you just taking this new notation and not really explaining it. I hope that in Cal 2, your instructor will take time to explain why we use this symbol, but I'll tell you briefly, and I mean briefly, where it comes from. Well, I'll do it up here. There's no need to not have it written down. What it turns out to be is that in Cal 1, we're trying to find the slope of the tangent line, right? Given a function, little f, the slope of this line is equal to the derivative of that function. Yes? That's the relationship between little f and its derivative in Cal 1. In Cal 2, what we realize is that if you take little f and you take its antiderivative, right, you can actually find the area underneath that curve. Now, that's very important because the area underneath the curve can have lots of different meanings. You have, in physics, you apply a force onto an object over a certain distance, then you graph that. If you take the area underneath, it gives you the total work done. It computes your work. Or it can be a lot of different things. So we are very interested in finding the areas under curves. That is tied into the antiderivative. But the symbol, the integral symbol, comes from the idea that if you want to find this area, right, if I want to find that area, what I do is I cut it into a bunch of rectangles. and I get the area of rectangles, because we're good at finding areas of rectangles, right? Length times width, length times width. And what I realize when I do this, I have a bunch of error in here, like I'm missing pieces of the function, because the function's curved, my rectangles are perpendicular, aren't they? And so what I do is I cut it into more and more rectangles. I said I would be brief, but I lied. Here's a function. I want to estimate the area underneath this function. So what I do is I start cutting it into rectangles, right? If I add up the area of these rectangles, is that more or less than the area underneath this blue curve? More. So you can see my estimated area is 51.36. The true area is 41.33. Don't ask me how I got that, but it is. If I want a better estimate, what do? More rectangles. In fact, the more I have, the closer I get to the real value, right? But this is calculus. We know how to let things go to infinity, don't we? So what we do is in Cal 2, we actually let the number of these go to infinity. We take a limit and we let the number of rectangles go to infinity. And we add them all up, right? You want to add up all these things? Okay, so what's the notation that you use when you want to add things up? Have you seen that before? Sigma notation? The sigma notation is used to do a sum, right? But we don't want a finite sum. We want actually the sum of an infinite number of rectangles. So when we let the number of rectangles go to infinity, we change that symbol into this symbol. And so what we're seeing here, which unfortunately I don't have the time to go into, is that this integral sign actually comes from the idea that the area underneath this curve is actually computed by finding its antiderivative. So this sum that we're looking for is actually connected to that antiderivative, if we can find it. All right, hopefully your Cal 2 instructor will spend some time on what's called Riemann sums and explain that a little more to you. For me, I just want you to see antiderivatives right now. All right, you ready? Now we get into, yes. Yes. Yep. I'm looking forward to telling you. All right. So let's get back to that tangent problem that we had trouble with, right? So that's another way of me asking you to find the antiderivative of tangent, right? We are now I'm going to introduce you to this will be the last thing we do in this class, the last topic. It's integration, but it's a special type of integration. Right now, you only know how to integrate things two ways. You either knew the antiderivative because you know the derivative, right? Like 2x, you knew the antiderivative was x squared, or cosine, you knew the antiderivative of cosine was sine. You either knew it or you used the power rule, right? It's the only thing we've got. This, not so much. That's not power rule. It's not something you know the antiderivative of. So what technique can we use to try and get this? The first technique of integration is called substitution. After substitution comes integration by parts. After integration by parts comes trig integrals, then trig substitution, then partial fraction decomposition. There's 5 techniques of integration. You spend the first, third of Cal 2 suffering through techniques of integration. This one's the easiest, but it is the most essential. You have to know substitution before you can do anything else. Okay, so how does substitution work? I'm going to use what's called substitution, or you'll hear it referred to as U sub. A lot of times we'll just get to the point where we just call it U sub. U substitution. I'm going to replace something with U, is basically what I'm getting at. That's what the technique is called, but here's how you actually employ it. You must find some function in the integrand and also identify its derivative in the integrand. All right, so let's talk about what I just said there. You're going to look at the integrand. You're going to look in there at what you have. You're going to try and see, do you see a function, anything, and its derivative in there somewhere? Do you see it? And then one last thing here. Avoid trapping the derivative part in denominator or roots, etc. You'll see what I mean by when I do another example. All right. So let's look at this. Tangent x. Do you see something in its derivative? Well, I see tangent, but I don't see its derivative there. What's the derivative of tangent? Secant squared x? I don't see it there, right? So the u sub is not looking very promising at this point, is it? But if I rewrite the integrand by using the fact that tangent is sine x over cosine x dx, always keep the dx there. It's your differential. You'll see its value in a second. Then now do you see something in its derivative? Yes? What do you see? What is the something you see, and what is its derivative that you see? Anyone? No, I'm saying just look in there. Do you see a function, and also you see its derivative sitting there somewhere too? Okay, what do you see, and what is its derivative? I'm asking you. You see sine x, and you see its derivative is cosine x. Yes? Does everyone see that? Sine x, and its derivative is cosine x. But what did I just say about avoiding? Avoid trapping the derivative part in the denominator. Okay, so you just chose sine x, and then the derivative part, cosine x, was trapped in the denominator. Avoid that. So, in other words, that didn't work. How about the other way? How about cosine x? What's the derivative of cosine x? Negative sine x. You don't quite have negative sine x, do you? But it's off by what, a constant? That's okay if we're off by a constant, because we can always make up for it. I could always write this as negative sine, and that's fine. So it's okay to be off by a constant. So once you have identified something in its derivative, and that derivative has not been trapped, what you do is you write down your u substitution. U is going to be equal to whatever you saw, which we said was cosine x. Does everyone understand why I'm not using sine? Anyone have a... Because the derivative of that would have been down in the denominator. You don't want that. Okay. U is equal to cosine x. I'm about to make a substitution. Everywhere that I see cosine x, I'm going to replace it with u, right? Now, don't write it down yet. I'm going to replace this with u. But if I'm going to replace this with u, then I'm going to have x's mixed in with u's, right? I need my entire integral to change from one variable to a different variable. So I need to be able to replace not only cosine x, I need to be able to replace everything. Everything has to be replaced. So what I'm going to do over here on this substitution is I'm going to work with this like an equation, and I'm going to go ahead and just take the derivative of both sides with respect to x. So what is the derivative of u with respect to x? Du dx. What is the derivative of cosine with respect to x? Negative sine x Do you agree? Now, isn't du dx the same as du times negative sine x dx? So I'm essentially multiplying both sides by the differential dx. Questions? Do you see the highlighted part here, dx, sine x dx, is exactly what this is right here? Do you see that? Now that dx is like dx over 1, so it's really on top with the sign, isn't it? That dx on the end? So that means that I can actually replace sine x dx with, not quite du, because I had a negative out here, didn't I? That's okay. Why don't I just multiply both sides of this equation by negative 1? Yes? So this equation right here becomes negative du equals sine x dx. It's an equation, right? I can multiply both sides of the equation by negative 1. Now that can be a direct replacement. I will replace sine x dx with what? Negative du. I will replace cosine x with what? U. And so what I want you to do is rewrite the entire problem now. I have an integral sign. What does the sine x dx become? Negative du. Over, what does cosine x become? U. Questions? Now, I'm going to just tweak this a little bit. This is the same as negative 1 over u du, isn't it? So I'm sliding that du back out on the outside so that again it looks again like an integral, right? Like this integration symbol. My du is keeping track of my variable, my differential outside, and I need to figure out what the antiderivative of this is. I'll do one more thing before I do the antiderivative. The negative is like a negative 1, isn't it? And remember that with taking a derivative and taking antiderivatives, both directions, constants can always come out front. That negative 1 is just going to come along for the ride, isn't it? When I take the antiderivative, it'll just follow me. What is the antiderivative of 1 over u? Natural log of u, right? But then I have a negative out front. So I have negative natural log u, right? What just happened? My symbol went away. Why did it go away? Because I found the antiderivative, right? And then the du went away. Everyone always asks me, where does the du go? It always goes away when you take the antiderivative. These are just, this right here and this right here are just telling you the operation of what you're doing. This is telling you, give me the antiderivative of this. Okay, here it is. There it is. No more symbols, right? They're gone. The negative does come, though. You okay with that? Are we done? Why not? Why? Yeah, because, I mean, you're asked for the antiderivative of the tangent of x function, and your answer is negative natural log of u. Right? That's like, I think I probably said it before. It's like me asking what your favorite color is, and you're like, strawberries. Exactly. You know, it doesn't make any sense. What's the antiderivative of tangent x? Natural log of u. What? So negative natural log of what? What's u? Come back up here, cosine x. Isn't that what I said it was? Didn't we check it? Plus c? Now I realize I'm the instructor. I should know this stuff, right? Right? I should obviously know how to do this. But when I showed you the antiderivative tangent of x as an example, I don't have a formula memorized. Okay, like I don't know, like I know the derivative of tangent is secant squared x, but I don't have it memorized the other way. So mentally, I did sine x over cosine x in my head, saw the u substitution, made the u substitution, saw it would be off by a sign, came in with it, 1 over u, all in my head. I understand I should be able to do that, right? But by the midpoint of Cal 2, you should be able to do that. in your head. All right? But the only way you get to that point is by doing many, 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 many U-sub problems. You have to do a lot to get that good. All right. Shall we do another? Absolutely. We still have 30 minutes of joy. All right, so how about this? U-sub, we'll keep it clean. Is that something you just look at and go, oh yeah, I know the antiderivative of that? It's not one of the obvious ones like cosine, antiderivative cosine, right? Is it power rule? Could you rewrite this as powers of x? You have to be careful. That denominator could be rewritten like that, right? But I don't think you're going to go anywhere from there, because that 1/2 cannot go to each one of these. Why not? Because there's addition there, right? Can't do that. And even if you did that, you could not then split it into two fractions, because you have a single term on the top and 2 on the bottom. It would work the other way around, but not that way. So there's just no hope that getting this to powers of x would ever work. So I pull out my next thing on my list of things to do, and U-sub would be the next thing. And so I'm trying to identify something in its derivative. It's okay to be off by a number, right? We were off by -1 last time. It was okay. We recovered from that. Do you see something in its derivative? What? Okay, so tell me what you want me to let U be. Exactly. What do you want me to let U be? You said it. X cubed. Is that all you want? I could do that, right? Let me see. How about this? I'm just going to write this next to it. Could I do this one? Is there any difference between doing these two? The +1. When I take the derivative of this, I'm going to get the same as when I take derivative of this, right? But there's an advantage to doing one over the other. If I use this one, when I replace this, I'm going to replace this with what? I'll have U plus 1, right? U plus 1 in here. And then I have the square root of U plus 1, which is still crappy. But if I use this, then I replace the whole thing with U, right? And then I have the square root of U. Square root of U is just U to the -1/2. Do you see the difference? Now, what about this? What if I try and get all gung-ho and say, you know what, I'm not only taking the x cubed and the +1, I'm going to take the square root also. What's wrong with doing it this way? What's its derivative? It's a mess, isn't it? Do you see its derivative here? No. Right, the derivative of this would require chain rule. 1/2 root x cubed plus 1, then times the derivative of what's inside. It would be too much, right? It's like a balancing act here. You want to grab a U that's enough to make a difference, but not so much that it blows the problem up, if that makes sense. So what's the correct one to use? X cubed plus 1. How do you get good at that? Practice. X cubed plus 1. All right. I will be able to replace this right here, not the root, but that right there will be replaced with U, won't it? That's going to be a direct substitution. That's going to become a square root of u. I'm happy about that. But I need to figure out what that x squared is going to become. So let's take the derivative over here on both sides. Du dx is what? What's the derivative of x cubed plus 1? 3x squared, right? And I'm really, really getting excited because x squared is right here, right? Isn't it? And so what I'd like to do is just try and make this side over here look like this, and I will always attach the dx to it. Remember how I said you don't want the derivative in the denominator? It's because I always want to attach the dx next to it. Because whenever I do this derivative on both sides, and I multiply by dx on both sides, the dx is always going to be right next to it, isn't it? On the right side, my next step. Right? Multiply both sides by dx. What am I off by here? 3. So I don't want that 3 there because that won't match what's up here. So what do I do here? Multiply both sides by 1/3 or divide both sides by 3 right here. So that'll turn into 1/3 du equals x squared dx. It's like a matching game. You're trying to make this piece here match with this piece here, and you have to manipulate things algebraically to make it match. I have a perfect match now, don't I? So help me rewrite this integral. Integral, what does the x squared dx turn into? 1/3 du, and that's up top, isn't it? Over square root of u, right? Replace this with u, so square root of u. What can I do with the 1/3? Because it's a constant. Just pull it out of the entire integral and just leave it out there like multiplication. So that's like a times out there. And then I'm going to rewrite this as 1 over the square root of u, and then slide that du to the outside. How am I going to handle finding the antiderivative of this? Rewrite it as u to the negative 1/2, right? So now I'm going to employ the power rule. But I first need to rewrite that 1 over root u as a u to the negative 1/2 du. You following me? U to the negative 1/2. What is the antiderivative of u to the negative 1/2? No, we haven't taken the antiderivative yet. We have to find the antiderivative first. So let me bring my 1/3 over here. This is like x to the n, isn't it? We've got this formula. So it'll be 1 over n plus 1, u to the n plus 1, because we're using u instead of x. So 1 over negative 1/2 plus 1, u to the negative 1/2 plus 1, plus a constant of integration. What do we got? Negative 1/2 plus 1, 1/2, 1 over 1/2, 2 times the third, 2/3. 2/3 u to the 1/2 plus a constant. Almost done. Now plug in u. What is u? X cubed plus 1 plus c. I just rewrote the 1/2 as a square root. Replace u with x cubed plus 1. What do you think? That's, well, yes, this is the beginning of u sub. This is, Yes. Yep. You could put the 2 out in front of the root and just put the whole thing over 3. Yep. Yes. Yes. I would probably take it back to this, this version. I would take it back to 2/3 x cubed plus 1 to the 1/2 plus c. That's the antiderivative, right? Now I take the derivative. I'm going to do it mentally. 1/2 comes out here. What's half of this? 2/6 or 1/3? 1/3. All of that to what power? Subtract 1. Times chain rule. What's the derivative? What's inside? 3x squared. What happens to the 1/3 and the 3? They cancel. You're left with x squared over the square root of x cubed plus 1. Right? What's that? It's easier going forward? Yeah, I know. Go run a marathon backwards. That's what Cal 2 is going to be. Okay? I mean, it is. But you can't, that's the thing I've been saying from the very beginning, is that Cal 2 is so much harder because it's backwards. But you can't do it unless you can go forward. Like, how are you ever supposed to see something in its derivative? You can never figure out derivatives. Whoa. You know what I'm saying? It's like, if you're still like at that point where the derivative of x to the 2/3 is something where you're like, I don't know, that was a long time ago, it's going to be a challenge. One of the things we've been talking about as a math faculty is that we want to start making all of our exams cumulative, where you're always including pieces of stuff from the past. Because what we're running into is that, you know, you walk into Cal 2, it's been so long since you've seen certain things that it's like you've forgotten it, which we understand that happens. But if you're testing on it, every test you're still keeping the main things in there, then it's less likely to be forgotten. The problem is then the tests, you know, become even longer, and how do you do that? It's impossible. Okay, let's see. This is a cool one. My first question to you is, can you use any rules that you know? Like, is this just a power rule? It's not, because this thing is raised to the 109th power, right? You cannot just do, oh, okay, I'm just going to do like this to the, 110, add a power up there and divide by 110, 1 over 110. You can't, because this right here is not just x, it's x plus 5. Now, could you, if you had enough time, could you take this and multiply it out? I mean, could you? You could if you'd like. Take x plus 5, right? And you could say, I'd like to expand x plus 5 to the 109th power. That's it right there. No problem, right? We could do that. And then we could actually find the antiderivative of each one of these, right? Because they're all powers of x. That's some huge number, right? Who cares? That's a constant. We just bring it with us. And then we would have like x, that's x to 74, so we do like 1 over 75 x to the 75. And we got to do that for each one of these, right? But you had to actually go through and expand that. X plus 5, 109 times. Not the option I would advise you take, or not the path I'd advise you take. But at the same time, if we can't do a simple power rule, it's not something we can identify and look and just say, oh yeah, it's this. Then all you have is u sub. But u sub says find something in its derivative. Do you see something in its derivative? So let's hear some candidates for something in its derivative, or something. What do you want your u to be? By the way, don't ever make a substitution that u equals x. If you do that, you'll rewrite the entire problem. You'll replace all your u's with x's, and you'll be in the exact same spot. Okay? So u equals x, no go. Anything else? X plus 5, do you see its derivative? Do you? Let's just look at the derivative. What is the derivative of this? What is the derivative of u with respect to x? What is it? Do you see a 1 there? They're everywhere, right? There's a 1 here and a 1 here. I mean, there's 1 out here. There's 1s everywhere. This does not look like it's going to help, does it? I mean, it doesn't look like that's going to get us anywhere. Through here, order of operations, right? Exponents goes before multiplication. So you have to expand all this before you pass the x through. So this does not look like it's going to produce results, right? But it is. So this is an example of when u substitution is not clear, but you do it and it works, which is unfortunately, for those of you who like order to things, this is an example where you just have to take a swing at it. And if you miss, you miss. If it works, it works. So let's just rewrite this. Du equals 1 dx, right? I'm working with this still. The derivative of u with respect to x was just 1, and then multiply both sides by dx. And that means I can replace dx with what? Du, right? I'm going to be able to replace dx exactly with du. So I'm good with that piece, right? I'm also going to be able to replace x plus 5 with what? U. The problem is, what do I replace x with? Drum roll. U minus 5. Because this is an equation, isn't it? Yes? So u minus 5 is x, isn't it? Correct? And this is going to be absolutely beautiful what happens. All right? Our problem of raising this thing to the 109th power is about to completely vanish, as you see when I rewrite it. Does everyone understand where I got this from? Just subtract 5 on both sides? Okay, so what am I replacing x with? U minus 5, so let's write it down. U minus 5. What am I replacing x plus 5 with? U. So that's just u to what power? 109. Now what am I replacing dx with? Du. Do you see how that just totally got us around the problem? Because this u to the 109 can be passed through this parentheses now. Because there's no power on this parenthesis. Right? So let's multiply this through. What would you get? U to the what? 110 minus 5u to the 109 du. Are you going to be able to find the antiderivative of this? Yes, because this is just two separate terms, right? Each of those power rule. What is the antiderivative of u to the 110 power? Integral sign's gone now, right? I'm doing the antiderivative. Integral sign's going to go away. Du is going to go away. Antiderivative of this is 1 over 110 plus 1, so 111. U to the 110 plus 1, so 111. Minus 5 over what? 110. U to the 110 plus constant. If it makes you happy, imagine that the integral sign and the du all go away and the c is what takes its place. If that makes you feel better about life. All right? Am I done? replace u. What's u? X plus 5. X plus 5 to the 111th power minus, reduce that fraction. 1 over 22, is that right? X plus 5 to the 110 plus c. I'm sad it's coming to an end. We only have 10 minutes. This is just now starting to get fun. I'm sorry? No, this is it. I mean, I'd love to. If y'all want to, we can. We can keep going. No? Damn it. In Cal 2, depending on your instructor, Cal 2, I mean, I always start out assuming a student has never seen integration. But a lot of times, I mean, our course description, we are supposed to cover antiderivatives, and we are supposed to cover like U sub should be in there. So that's why, I mean, we've done it. We've just touched the surface here on integration. By no means are you're still a novice, okay? I mean, there's still a long way to go with this, all right? What we've done in like 40 minutes is not Cal 2, all right? But it gives you an idea. So I would like for you to take a look, if I could borrow this real quick. All right. We have these reference sheets, right? And reference sheet 5 had all the derivative formulas on it, right? It showed you what the derivative was. Flip over to 6, and now what you're going to see are antiderivative formulas, integral formulas, right? Okay. What's that? They use different tangent? What? Oh. That's a good, I'll point this out. This is nice. If you look at this, it says antiderivative of tangent x dx is equal to natural log absolute value secant, well, they use u, but I'll use x, plus c. That's not what we got, right? What did we get? We got negative natural log of what? Cosine x. Do you remember the property of logs? That if you have a number out front, you can bring that number up as a power. Put that power on cosine. What is cosine raised to the negative 1? 1 over cosine. What's 1 over cosine? Secant. It's all in there. Okay, so look, you see that formula sheet? If you have the book, reference page 6, that's on your formula sheets, is this page. What's not in there is reference page 7, 8, 9, and 10, which are all integral formulas. In fact, you could find a book this thick full of integral formulas, because going backwards is so difficult that there are a lot of integrals that have been worked out already in general, so you don't have to do them. Differentiation, there's only one page. Look, we've got power rule, product rule, quotient rule, chain rule. That's it. Derivatives, it's straightforward, man. There's no voodoo magic going on. Going backwards, there's a lot. I was looking for something in the book because this author doesn't say it, but there was another author that when they got to the integration chapter, they said, look, up to this point, Cal 1's very straightforward. Differentiation, very straightforward. This integration is a lot of pulling rabbit out of hat type thing. Like this thing we did here is not necessarily a natural move. It didn't look like it was going to produce a result for us, but it did. So when you get into integration in Cal 2, you're going to fail more times than you're going to succeed. You're going to fail to get the antiderivative. The substitution you make is not going to work. The question is, are you going to quit or are you going to keep trying? because that's what's going to separate you from everyone else, is whether or not you're going to keep going, trying something else until it works. Understand? All right. 5 minutes. Yes. I knew what to do. I probably could have resolved the numbers if I thought about it, but yeah. It's a classic example. So you should have some homework to practice, right? Of course. This is stuff's going to be on the test, on the final, so antiderivatives, yes. You thought it was for fun or what? You just, hey man, we're just having fun in here. Look, please, we're not doing Cal 2, this is Cal 1. There's an overlap in Cal 1. If you read the description of Cal 1, it is. I don't want you all to feel like I'm cheating you out here and like I'm screwing you all over. Come on, get out of here. Okay. Evaluate definite integrals using fundamental theorem of calculus. We didn't even touch that. Articulate the relationship between derivative and integrals using fundamental theorem of calculus. We didn't even do that. Okay. This requires antiderivatives. You have to know integration to do this. Where's the... See? Antiderivatives evaluation theorem. That's what I'm talking about now. We didn't do evaluation theorem. Right? What's that? Yeah. But you're good. I mean, you're okay. I mean, I think if you've seen this, knowing how to find antiderivatives, the rest of it's going to be okay. This is the most critical part, is that you can at least take an antiderivative of a power function or something. So your suggested homework is page 289. I'm just looking at when I should stop. Okay, 1 to 17. All right, and I have to point this out because all of these problems are going to have these little things. It'll be like -1 to 2, and then it'll have like x squared plus x, and then it'll say like dx. And I did not talk to you at all about what these numbers mean, so I want you to completely ignore them and act like they're not there. And so what that's saying is find the antiderivative of x squared plus x, right? So your answer would be 1/3 x cubed plus 1/2 x plus c, and you'd be done, right? Right? That's what you would do. But that doesn't match what the back of the book's going to have as an answer, because with the numbers on there, you're actually finding that area that I was talking about. But we didn't talk about that yet. We were still focusing on techniques. So see how you do on 1 through 17. That's all just derivatives, or antiderivatives. That has no substitution in it. If you would like to practice substitution, go to page 306 and look at problems 1 through 19. Again, those don't have numbers on them at all. So keep in mind when you're doing your work, this is all U substitution problems. So you should approach them that way. This is all power rule, or it's a formula you already know. That's what it's going to be. All right, well, I'll see you on Thursday.